You step onto a ship that will not turn around. Not because you are forced to stay, because turning around would take longer than the rest of your life. 40 light-years away, a small red star holds 7 worlds in a tight, quiet orbit. 3 of them sitting in the narrow band where water might still be liquid. 40 light-years sounds like a number you could say out loud and move on from. It is not. It is 384 trillion kilometers. The fastest object humanity has ever launched has covered a sliver of that distance too small to round up to 1%. But here is the part most people get wrong. The problem was never really the distance. The real problem is everything distance quietly breaks along the way. The fuel, the body, the mind, the very idea of who is still you by the time you arrive, if anyone arrives at all. If you enjoy deep space and science content, do me a small favor and hit subscribe. Get yourself comfortable. Let's begin. To understand why this journey would be so difficult, it helps to understand how strange it was that we ever found this place at all. In the autumn of 2015, a small telescope in the high, dry mountains of Chile was watching one star. Not a famous one, not a bright one. The telescope was called TRAPPIST, an awkward acronym, the kind scientists are fond of, and it had been built to do one narrow job. It watched faint, cool, red stars known as ultracool dwarfs, hoping to catch the tiny dimming that happens when a planet crosses in front of one. For 62 nights, across 245 hours, it watched a star now called TRAPPIST-1 in the constellation Aquarius. And the light dimmed, not once, repeatedly, in patterns too regular to be noise, too layered to be one planet. A Belgian astrophysicist named Gillon at the University of Liège led the team untangling what they were seeing. By May of 2016, they were confident enough to announce 3 planets. That alone would have been a notable year for the field. But the data kept insisting there was more hiding in the overlaps. Follow-up observations using NASA's Spitzer Space Telescope and several ground-based instruments kept splitting what looked like one signal into 2, then more. By February of 2017, when the full result was published in the journal Nature, the count had reached 7. 7 roughly Earth-sized worlds, orbiting one small star, packed into a space tighter than the orbit of Mercury around our own Sun. The method behind this discovery is, in its own way, a small miracle of patience. Astronomers cannot see these planets directly. They are far too small, far too dim, far too close to the blinding presence of their star to be picked out individually, even by our best instruments. What they can see is the star's light dimming, ever so slightly, when a planet happens to pass directly between that star and our telescopes. It is the same principle as watching a porch light from across a street and noticing it flicker each time a moth crosses in front of the bulb. One flicker could be anything: a cloud, a glitch, a trick of the instrument. But a flicker that repeats on a fixed schedule, again and again, with the same depth and the same duration, stops being noise and starts being a planet. TRAPPIST-1 gave its observers 11 such flickers across those 62 nights, each dimming the star's light by about 1%, small enough to miss if you were not looking closely, regular enough to trust once you were. Part of why this particular star was worth that kind of patient attention has to do with what kind of star it is. TRAPPIST-1 is what astronomers call an ultra-cool red dwarf. Small, dim, barely larger across than the planet Jupiter, and burning at a fraction of the temperature of our own Sun. Stars like this are, by a wide margin, the most common type of star in the galaxy. The Milky Way is built mostly of small, cool red stars rather than bright yellow ones like ours. That matters for a planet hunter for a simple reason. A dim star makes a small planet's shadow easier to detect, proportionally, the same way a single candle in a dark room reveals far more about what crosses in front of it than a spotlight does. TRAPPIST-1's dimness was not a limitation. It was the reason the 7 planets were findable at all. For a public used to hearing about exoplanets as distant points of light with vague, hopeful labels, potentially habitable, Earth-like, could support life, TRAPPIST-1 felt different. It felt like a neighborhood. 3 of the 7 planets named E, F, and G sit inside what astronomers call the habitable zone, the band around a star where temperatures allow liquid water to exist on a surface instead of freezing solid or boiling away. 3 chances in one system. Some years, astronomers are happy to find one such candidate anywhere in the sky. TRAPPIST-1 offered 3, possibly 4, in a single afternoon's data review. It is worth sitting with why that felt so significant, and also why it can be slightly misleading. Earth-sized is a measurement of radius. It says a planet is roughly the same size as ours, nothing more. It says nothing about the air above its surface, the chemistry of its rock, the violence or calm of the star it orbits. A planet can be precisely Earth's size, and nothing else about it familiar at all. The word does a great deal of emotional work for a single physical fact, and it is easy, hearing it, to picture a porch light from home rather than an unknown world. There is something almost domestic about the TRAPPIST-1 system once you look at the numbers closely. All 7 planets together would fit, comfortably, inside the orbit that Mercury traces around our Sun. 7 worlds, occupying a region of space we would consider, in our own solar system, too cramped for even 2. It resembles, more than anything, a miniature solar system scaled down to fit in a drawer. The kind of closeness that makes a place feel reachable, almost walkable, in the way a cul-de-sac feels walkable compared to a country. But closeness on a star chart and closeness in the real, physical universe are not the same kind of distance. And that gap between how near TRAPPIST-1 looks on paper and how far it actually is in kilometers, in years, in the limits of physics, is where this story actually begins. 40.66 light-years. That is the figure astronomers currently use for TRAPPIST-1's distance from us, and it is worth slowing down on what a light-year actually is before the number means anything at all. A light-year is not a unit of time, despite the word sitting right there in the middle of it. It is a unit of distance, specifically the distance light travels in 1 year, moving at roughly 300,000 kilometers every single second. Light leaves the sun and reaches your eyes in about 8 minutes. Light leaving TRAPPIST-1 takes over 40 years to reach the same eyes. Every photon currently arriving from that star left it sometime in the mid-1980s, long before most of the people watching this video were born, and it has been traveling, uninterrupted, ever since. Translate that into kilometers, and the number stops being elegant and starts being almost absurd to say out loud. 40.66 light-years comes to approximately 384 trillion kilometers. For context, that is the distance you would cover driving a car at a constant highway speed of 100 kilometers an hour without ever stopping for roughly 440 million years. Civilizations would rise and end before that drive was finished. It is also, separately, about 2.5 million times the distance between the Earth and the Sun, a distance we already consider, in ordinary human terms, almost incomprehensibly far. There is a more honest way to feel this number, though. And it does not require imagining a car at all. It requires looking at what humanity has actually managed to send out into the dark and how far that has gotten. In September of 1977, a spacecraft called Voyager 1 left Earth. Its mission, on paper, was modest. Fly past Jupiter and Saturn, take pictures, measure what could be measured, and report back. It carried a golden record, an actual gold-plated copper disc, etched with greetings in 55 languages, recordings of whale song, bird song, a heartbeat, fragments of music from Bach to Chuck Berry, all chosen as a kind of farewell letter in case anything ever found it adrift. Carl Sagan led the small NASA committee responsible for choosing what went on that disk, working under genuine time pressure. By some accounts, the team had less than 6 weeks to decide how to summarize the entire population, history, and culture of a planet, in case it was ever discovered by an intelligence none of them could imagine. The physicist Frank Drake suggested the format itself. Pictures on one side, sounds on the other, etched into a medium that could, in principle, survive intact for longer than human civilization itself has existed. Sagan reportedly believed it was far more likely to drift forever, unfound, than to ever be encountered by anyone capable of understanding it. It was not built with TRAPPIST-1 in mind. Nothing about its trajectory points toward that star at all. In fact, Voyager 1 is not headed toward any particular destination. In roughly 40,000 years, it will simply pass, within a light year or so, of a faint star called Gliese 445, currently visible in the constellation Camelopardalis, and continue on, unaffected, into the dark beyond. Nearly 50 years later, Voyager 1 is still moving, still transmitting, somewhere beyond the outer edge of our solar system, in the region scientists call interstellar space. Its speed is genuinely fast by any everyday measure, over 60,000 kilometers an hour, fast enough to cross the distance between New York and London in a few minutes. And in nearly half a century of that speed, sustained, uninterrupted, it has covered a distance equal to a small fraction of 1% of the way to even our nearest stellar neighbor, let alone TRAPPIST-1, which sits roughly 10 times farther away than that. Voyager 1 is not failing at its job. It has succeeded beyond what its engineers likely expected, and remains, after almost 5 decades, capable of sending back data from farther away than any human-made object has ever traveled. It is simply a measurement of just how large the gap actually is, carried out by the fastest thing we have ever built and sustained for the longest period of time we have ever sustained it. In simple terms, if Voyager 1 had been launched directly at TRAPPIST-1 instead of toward the outer planets and never slowed down, it would still take in excess of 700,000 years to arrive. Multiple ice ages would pass. The shape of human language would change beyond recognition more than once before that spacecraft completed the trip. NASA's New Horizons probe, launched in 2006 specifically because it needed to be fast. Its mission required reaching Pluto in a single human lifetime, left Earth faster than Voyager did. And even New Horizons, the fastest launch speed humanity has ever achieved directly from the ground, would still require several tens of thousands of years to cover the same distance. Speeding up the launch helps. It does not solve the problem. It only changes how many zeros come after the number. This is the quiet, unglamorous truth sitting underneath every hopeful headline about TRAPPIST-1's potentially habitable planets. It is not that the destination is unreachable in principle. It is that nothing we have ever built, launched, or seriously proposed comes anywhere close to making the arithmetic survivable within a human lifetime, or several. Which raises the obvious next question. Not whether we could go faster, but how much faster, and what kind of engine that would actually require. So the obvious question becomes, what if we simply built something faster? It is worth walking through the real options on the table, because each one fails for a slightly different reason, and the pattern in those failures is more revealing than any single number. Start with the most familiar kind of rocket, the chemical rocket, the same basic family of engine that has carried every human being who has ever left Earth's surface. Chemical rockets work by burning fuel and expelling the exhaust at high speed out the back. And the speed of that exhaust is, fundamentally, the ceiling on how fast the rocket itself can ever go. For chemical fuel, that exhaust speed tops out at a few kilometers per second. To go faster than that, you need more fuel, but more fuel adds more mass, and more mass needs more fuel to move it, which adds more mass again. The relationship is not gentle, it is exponential. Push a chemical rocket's required speed high enough, and the fuel mass needed stops being something you could build a rocket around and becomes something closer to a small planet's worth of propellant. This is not a hypothetical concern dreamed up to make the problem sound dramatic. It is the same equation, unmodified, that NASA uses to plan every mission it has ever launched. Chemical propulsion gets us to the moon. It does not get us, even loosely, toward another star. The next idea sounds almost violent by comparison, and in some ways, it is. In the late 1950s and early 1960s, a real American research effort called Project Orion, led by physicist Ted Taylor and theoretical physicist Freeman Dyson at General Atomics, explored the idea of propelling a spacecraft by detonating small nuclear explosives behind it, in sequence, and riding the shock waves forward, like a surfer riding a wave that never stops arriving. The design called for ejecting a small nuclear charge, detonating it some distance behind the craft, and letting a heavy metal pusher plate absorb the blast, transmitting that force forward through a system of shock absorbers smooth enough, in theory, for a human crew to survive the ride. Some early designs called for nearly one detonation every second during the initial launch phase, an idea that sounds almost reckless, stated plainly, and yet the underlying physics held up to serious scrutiny. On paper, the physics actually checks out reasonably well. Nuclear pulse propulsion offers far more energy per unit of fuel than chemical burning ever could, with some theoretical estimates of its efficiency running 10 to 100 times higher than even advanced chemical rockets. The project employed real physicists, produced real engineering studies, conducted a real subscale flight test using conventional explosives in 1959 to prove the concept of stable, controlled pulses, and was taken seriously enough to be funded for years. It was eventually abandoned, partly over practical engineering hurdles, and partly because of a 1963 international treaty banning nuclear detonations in the atmosphere and in space, a political ceiling sitting directly on top of a technical one. Even setting the politics aside, the energy gains from nuclear pulse propulsion, while real, still fall dramatically short of what would be needed to cross 40 light-years within a human lifetime. A later, more refined version of the same basic idea, a 1970s study called Project Daedalus, proposed an unmanned probe driven by a different kind of nuclear reaction entirely, fusion rather than fission, theoretically capable of reaching roughly 12% of the speed of light. Even at that improved speed, the study's own target was Barnard's star, just under 6 light-years away. TRAPPIST-1 sits more than 6 times farther than that. Then there are ion drives, which represent something closer to the opposite philosophy. Rather than a single violent burn, an ion engine accelerates a small stream of charged particles continuously, for months or years at a time, building speed the way a marble might build speed, rolling very, very slowly down an extremely long hill. NASA's Dawn mission, which explored the asteroids Vesta and Ceres, used exactly this kind of engine, and it remains one of the most fuel-efficient propulsion systems ever flown. Ion drives are remarkable for what they are designed to do. What they are not designed to do is reach any meaningful fraction of the speed of light. Their thrust at any given moment is famously gentle, often compared to the pressure of a sheet of paper resting on your hand. Patience alone cannot make up for that gap when the destination is 40 light-years away. This is where a more recent, more ambitious idea enters the picture: light itself as the engine. In 2016, a research initiative called Breakthrough Starshot proposed building an array of ground-based lasers, generating roughly 100 gigawatts of combined power, and aiming that beam at a fleet of gram-scale spacecraft, each fitted with an ultra-thin reflective sail only a few meters wide. The idea was to push these tiny sails to around 20% of the speed of light, using nothing but the pressure of photons striking a mirror. Fast enough, in theory, to reach our nearest stellar neighbor within about 20 years of launch. It was, and still is, one of the more genuinely promising interstellar propulsion concepts ever proposed. And it attracted real funding, real engineering papers, and real public attention. To put what 20% of light speed actually means in human terms, a spacecraft moving at that velocity would cross the distance from Earth to the Moon in roughly 6 seconds. But promising on paper is not the same as solved, and Breakthrough Starshot has, in the years since its announcement, quietly lost much of its early momentum. The engineering obstacles turned out to be substantial, keeping a sail just a few atoms thick stable and intact, while being pushed by a beam powerful enough to vaporize most materials outright, managing the heat that beam generates, steering a fleet of microscopic spacecraft precisely enough to actually hit a target light-years away. None of these problems are necessarily unsolvable, but none of them have been solved either, and the public funding and headlines that once surrounded the project have faded considerably. And even Breakthrough Starshot, even at its full, never yet achieved 20% of light speed, was designed with Alpha Centauri in mind, our nearest stellar neighbor, roughly 4 light-years away. TRAPPIST-1 sits 10 times farther out than that. The same engine, the same laser array, the same theoretical sail, scaled to this destination, would still mean a journey measured in centuries, not decades. Every propulsion concept humanity has seriously built, tested, or proposed shares the same shape of failure. Each one solves part of the problem and runs directly into a different wall further down the equation, which leads to the part of this problem that turns out to be even less forgiving than the engine itself, the fuel that engine would actually need to carry. There is a piece of mathematics that every aerospace engineer learns early, and it has a way of quietly ending conversations about interstellar travel before they really begin. It is called the rocket equation, and in plain terms, it describes an unforgiving relationship. The faster you want your final speed to be, the more fuel you need. And that fuel itself has mass, which then needs its own fuel to move it, and so on, compounding until the numbers stop behaving like anything you could build a spacecraft around. Consider just how harsh this becomes at meaningful interstellar speeds. to accelerate a single kilogram of mass to even 1% of the speed of light using a chemical rocket would require more fuel than exists. In total, across the observable amount of matter we know how to produce on Earth in a reasonable time frame. This is not an exaggeration written for effect. It is the direct output of an equation NASA itself uses for every real mission. Now imagine the actual mass of a spacecraft meant to carry human beings, life support, food and shielding across 40 light years, and ask the equation to scale accordingly. The fuel requirement does not simply get larger. It becomes a number with no practical meaning at all, the mathematical equivalent of asking how many grains of sand it would take to outweigh a star. This is the softening truth tucked inside a hard equation. The distance to TRAPPIST-1 was never really the obstacle. The obstacle is what it costs in raw fuel mass to cross that distance in any reasonable span of time. Distance is a number on a map. Fuel mass is a number that grows faster than any engine we have ever devised can outpace. A real engineering study makes this concrete in a way that is easy to picture. In the 1970s, a team at the British Interplanetary Society designed, in serious technical detail, an unmanned probe called Daedalus, intended to reach Barnard's star, just under 6 light-years away, using fusion-based propulsion rather than the chemical or fission methods discussed earlier. The final design called for a 2-stage vehicle roughly 190 meters tall, comparable to a 50-story building lying on its side, and it would have required approximately 50,000 tons of fuel to reach its theoretical top speed of about 12% of the speed of light. Even at that speed, the journey to Barnard's star alone was projected to take roughly 50 years for an unmanned probe carrying no crew, no life support, and no return journey home. TRAPPIST-1 sits more than 6 times farther away than Barnard's star. Scale the same design accordingly, and the fuel requirement does not simply multiply. It compounds, the same way compounding interest on a debt grows faster the longer it is allowed to run, until the number stops resembling anything an engineering team could reasonably propose building at all. So, scientists naturally have looked for a loophole. Some form of fuel so energy-dense that the usual exponential curse might finally bend. And in theory, one exists. It is called antimatter, and it is, as far as physics currently understands, the most energy-dense substance that could ever exist. When matter and antimatter meet, they do not simply react. They annihilate completely, converting the entire mass of both into pure energy, with none of the waste or inefficiency of ordinary chemical or even nuclear reactions. A single gram of antimatter, fully annihilated against an equal gram of ordinary matter, would release an amount of energy comparable to a small nuclear weapon. In theoretical terms, it is the cleanest, most efficient fuel imaginable. An antimatter-driven engine could, on paper, approach a meaningful fraction of the speed of light, using a fraction of the fuel mass any chemical or nuclear engine would need. But theory and inventory are very different things. Humanity does not have antimatter sitting in a warehouse. We have to manufacture it, one antiproton at a time, inside particle accelerators built for entirely different research purposes. CERN's antiproton decelerator, one of the few facilities on Earth capable of producing antimatter at all, generates it in quantities measured in nanograms, billionths of a gram, over the course of a full year of continuous operation. The cost of that production, scaled up, comes to a figure NASA's own technical reports have cited directly, approximately $62.5 trillion per gram. To put that in human terms, at current global production rates and current cost, acquiring even a single gram of antimatter, roughly the mass of a paperclip, would take longer than the universe itself has existed and cost more than the combined economic output of every nation on Earth several times over. A spacecraft capable of meaningfully using antimatter propulsion across interstellar distances would likely require not grams, but kilograms. The gap between what we can currently produce and what such a journey would require is not a gap measured in funding or political will. It is a gap measured in the basic physical capacity of human civilization to manufacture matter, atom by atom, faster than we currently know how. None of this means antimatter propulsion is fiction. The physics is real, peer-reviewed, and taken seriously by serious institutions, including NASA itself, which has published technical studies on antimatter propulsion concepts. What it means is that the fuel problem and the engine problem are, in practice, the same problem wearing two different names. Even if humanity solved every engineering challenge in building the perfect interstellar engine tomorrow, it would still need a fuel source that does not yet exist in any usable quantity, manufactured by a process so inefficient that producing enough of it would, by some honest estimates, outlast our species. And even setting fuel aside entirely, even imagining, for the sake of the thought experiment, that some future civilization solves this, there remains a problem that no amount of fuel, no matter how dense, can fix. Time itself behaves differently the closer you get to the speed of light. And that single fact changes who exactly would be making this journey at all. There is a strange and easily overlooked fact about time, and you carry proof of it in your pocket every day, whether you have ever thought about it or not. The satellites that make up the global positioning system orbit Earth at roughly 14,000 kilometers an hour, far higher and far faster than anything on the ground. Albert Einstein's theories of relativity predict, with mathematical precision, that clocks moving at that speed and sitting that much farther from Earth's gravity will tick at a very slightly different rate than clocks down here on the surface. Not slower in some vague philosophical sense, measurably physically different. Faster in this case by about 38 microseconds per day, once the competing effects of speed and gravity are combined. 38 microseconds sounds, on its face, like nothing at all. But left uncorrected, that tiny daily drift would cause GPS positioning errors of around 10 kilometers within a single day. The blue dot on your phone, the directions guiding you home, the entire system depends on engineers having accounted for the fact that time itself runs at a different rate up there than it does down here. This is not a thought experiment. It is built into hardware currently orbiting above your head. Now take that same effect, real, measured, already correcting your phone's GPS as you listen to this, and scale it up to the speeds an interstellar journey would actually require. Special relativity predicts that as an object's speed approaches the speed of light, time for that object, relative to a stationary observer, slows down, not because of some mechanical failure in a ship's clocks. Time itself, in a very real sense, passes more slowly for whoever or whatever is moving that fast, when measured against someone who stayed behind. The closer you get to light speed, the more dramatic this divergence becomes. At 20% of light speed, the velocity breakthrough starshot once hoped to achieve, the effect remains small, measured in fractions of a percent. But the propulsion concepts that could realistically close a 40 light-year gap within a human lifetime would require speeds far closer to light itself than anything proposed so far. And at those speeds, the divergence stops being a rounding error and starts becoming the entire story. Imagine, for a moment, that some future engine allowed a crew to travel at a substantial fraction of the speed of light, close enough that years passed differently for the people on board than for everyone left behind. A journey that feels, to the crew, like 20 or 30 years of lived experience, eating meals, raising children, growing old together in close quarters, could correspond to a far longer span of time back on Earth. Decades stretching into centuries, depending on how close to light speed the ship actually traveled. The travelers age normally by their own clocks. Earth, watching from a distance, ages faster. This creates a quiet, devastating asymmetry, even setting fuel and engines aside entirely. The people who step onto a ship bound for TRAPPIST-1 are very likely not the people who would experience arrival. If a journey takes even several decades from the crew's own perspective, let alone centuries at slower, more realistic speeds, the original travelers would, in many proposed mission designs, be dead long before any landing. This is the entire premise behind what mission planners call a generation ship. Not a vehicle built to deliver a fixed crew to a destination, but a closed, self-sustaining society built to deliver descendants. The people who arrive, under most realistic proposals, would be the grandchildren or great-grandchildren of the people who left. Born on board, raised on board, having never once stood on solid ground that did not move beneath them, inheriting a destination they did not choose, and a home planet they would only ever know through stories and stored data. Researchers who study this question seriously, using population genetics rather than imagination alone, have tried to calculate the actual minimum number of people such a ship would need to carry to avoid a slow collapse into inbreeding and genetic disease across the generations of the voyage. The estimates vary considerably depending on the assumptions used, which is itself revealing. This is not a settled engineering question with one clean answer, but an open and actively studied problem. Some of the earliest calculations, using simplified models, suggested a few hundred people might suffice, organized along the lines of small hunter-gatherer clans, with strict rules against close-kin reproduction. More recent and more cautious analyses, accounting for the realistic risk of disease outbreaks, accidents, and fluctuating birth rates across centuries rather than a single fixed snapshot, have pushed that number dramatically higher, into the thousands, and in some published estimates, into the tens of thousands, simply to ensure enough genetic diversity survives, intact across enough generations to remain viable on arrival. One detailed analysis modeling a multi-generational crew under realistic constraints found that a population below a few hundred would remain perpetually on the edge of extinction following even a single serious setback, while a healthier, more resilient outcome required a starting population closer to 10,000 people or more. Sit with that number for a moment, the way you might sit with it if it were your own decision to make. This is not a ship carrying a small, brave crew of explorers. Under many serious proposals, it is closer to a small city, sealed permanently inside a hull, expected to govern itself, feed itself, educate itself, and reproduce successfully across an unbroken chain of generations, with no possibility of immigration, no possibility of return, and no margin for the kind of disaster that, on Earth, a neighboring town or nation might help absorb. You are not deciding whether you, personally, would survive the journey. You are deciding whether to commit children who do not yet exist, and their children after them, to a sealed metal world, crossing an ocean of nothing, on your behalf. Every value you hold, every culture, every memory of Earth, would have to be preserved deliberately, generation after generation, by people who never asked to carry it. even if every fuel problem were solved tomorrow, even if some impossible engine appeared, fully formed, ready to fly, time itself would still demand a price that no amount of funding or ambition could simply pay off. And that price is not measured only in years. It is measured in the bodies that would have to survive those years, sealed inside a ship, with no way to step outside, breathe unfiltered air, or undo a single mistake. Suppose, for the sake of the thought experiment, that every problem so far has somehow been solved. The engine exists, the fuel exists, the crew has accepted the relativistic asymmetry, knowing their descendants, not themselves, will likely see a rival. There remains one more obstacle, and it is the quietest, least dramatic, and in some ways most stubborn of them all. The human body itself was simply never built for this. We already have real, measured data on what happens to the human body in space, because astronauts have been living on the International Space Station in increasingly long stretches for over 2 decades. The picture that data paints is not subtle. Bone mineral density, in the absence of Earth's gravity pulling against the skeleton during every step, every stand, every ordinary motion of daily life, begins to decline almost immediately. NASA's own long-term studies place that loss at roughly 1 to 1.5% per month, concentrated most heavily in the lower spine, hips, and legs, the very bones that, on Earth, bear the most weight and therefore lose the most strength once that weight disappears. A 6-month mission to the International Space Station, well within current medical monitoring, can leave an astronaut with a measurable, lasting deficit. One detailed study following astronauts a full year after their return found several had still not recovered their pre-flight bone density at all, with effects in some cases resembling a decade or more of ordinary Earthbound aging compressed into a single mission. In simple terms, spending months in microgravity ages parts of your skeleton the way decades on Earth might. Now multiply that exposure not by months, but by years, or by the lifetime of a single generation aboard a ship bound for another star. Muscle tissue follows a similar pattern. Without gravity to work against, muscles, particularly the ones that keep us upright and balanced, in the back, thighs, and calves, begin to weaken and shrink, sometimes losing significant size and strength within days of a mission's start, continuing to decline across its duration. Exercise regimens on the International Space Station, often 2 hours a day on specialized equipment, slow this decline considerably, but do not stop it entirely. A body in space is a body actively, continuously losing a quiet argument with its own design. Radiation presents an even starker problem, because here, Earth itself has been quietly protecting us all along, and most people never think to thank it. Our planet's magnetic field and thick atmosphere deflect and absorb the overwhelming majority of cosmic radiation and solar particle radiation before it ever reaches the ground. Astronauts aboard the International Space Station, still largely within that magnetic shield, absorb measurably more radiation than people on Earth's surface, but the real danger begins the moment a spacecraft leaves that protection behind entirely. Deep space radiation, unfiltered by any planetary shield, delivers a steady accumulation of exposure that increases long-term cancer risk and can damage the central nervous system in ways still being actively studied. A journey lasting years, let alone generations, conducted largely outside any planetary magnetic field, would expose a crew to a cumulative radiation dose far beyond anything currently considered survivable across a normal human lifespan, even with shielding technology far more advanced than anything currently deployed. There is a quieter, less publicized risk as well. One NASA itself has classified as one of its highest priority concerns for long missions, the effect of microgravity on the eyes. Astronauts returning from long-duration missions have been found, in documented clinical studies, to show swelling of the optic disc, flattening of the eyeball itself, folds in the tissue at the back of the eye, and measurable shifts in vision. Severe enough in some cases that astronauts have needed stronger reading glasses by the end of a mission than they needed at its start. Researchers believe this condition, now formally studied under the name spaceflight-associated neuroocular syndrome, stems from the simple absence of gravity's usual pull on bodily fluids. On Earth, gravity continuously draws blood and fluid downward, toward the legs and lower body. Remove that pull entirely for months at a time, and fluid instead shifts upward toward the head and eyes, in a way the human body never evolved to manage. Some of these changes, once thought temporary, have been documented persisting for years after a mission ends. It is a condition discovered almost by accident, simply because astronauts kept returning from the International Space Station, reporting that their vision had quietly, permanently changed. And then there is the simple, unglamorous mechanics of staying alive at all, for that long, without resupply. Every gram of breathable air, drinkable water, and edible food aboard a generation ship would need to be recycled again and again, indefinitely, by closed-loop life support systems with no Earth-based backup, no rescue mission, no spare parts shipment arriving next month. Even the International Space Station, supported by regular cargo deliveries from Earth and constant real-time engineering oversight, experiences equipment failures, air leaks, and life support glitches on a fairly routine basis. A ship bound for TRAPPIST-1 would need every one of those systems to function, essentially without major failure. Not for years, but for as long as it takes generations to be born, grow old, and pass that responsibility to their own children, without a single catastrophic failure along the way. This is not a problem solved by better engineering alone, though better engineering would certainly help. It is a problem rooted in something simpler and harder to fix. Human biology evolved over millions of years to function inside Earth's specific gravity, Earth's specific atmosphere, and Earth's specific protective shield against the radiation of space. Removing all three at once, for the length of time this journey would require, is not a minor inconvenience to be solved with the right gym equipment or the right water filter. It is asking a species shaped entirely by one planet to simply continue existing, generation after generation, somewhere that planet's most basic protections no longer apply. Even if a crew survived all of this, bones, muscles, radiation, recycled air, there remains one more form of distance this journey would impose, separate from kilometers and years entirely. The silence. There is a number that sounds almost too simple to matter, until you actually try to live inside it. A radio signal, like any form of light, travels at the speed of light, the fastest speed anything in the universe can move. That is, by any ordinary measure, astonishingly fast. It is also, when the destination is 40 light-years away, nowhere near fast enough to feel like a conversation. A message sent from a ship approaching TRAPPIST-1 back to Earth would take just over 40 years to arrive. A reply, sent immediately upon receipt, would take another 40 years to make its way back. A single exchange, a question asked, an answer given, would span roughly 80 years, start to finish. Anyone who asked the question would, in almost every realistic scenario, be long dead before the answer arrived. There is no version of real-time guidance, no mission control offering advice, mid-crisis. No quick check-in to ask whether a decision being made on board still matches what Earth would recommend. Once a ship is meaningfully on its way, it is, for every practical purpose, entirely on its own. Consider what that actually removes from the experience of the journey. Every space mission humanity has flown so far, from the first orbital flights to the International Space Station, has operated under the assumption that Earth is reachable, not instantly, but within minutes or, at the outside, hours. Mission control can intervene. Engineers on the ground can diagnose a malfunction the crew cannot see themselves. A crisis, however serious, exists within a shared conversation between the people in space and the people who sent them there. A generation ship bound for TRAPPIST-1 would have none of that. Every system failure, every medical emergency, every difficult decision about how to allocate dwindling resources would need to be solved entirely by the people on board, using only what knowledge, judgment, and equipment already existed within the ship's hull, because no answer from Earth could ever arrive in time to matter. We already have some real, if much smaller, sense of what sustained isolation does to people, because humans have tested versions of it here on Earth, both deliberately and, occasionally, by terrible accident. In 1915, Ernest Shackleton's ship Endurance became trapped and was eventually crushed by pack ice in the Weddell Sea, leaving 28 men stranded, first on the ship, then on drifting ice floes, then in small open lifeboats, for the better part of 2 years, with no radio, no means of contacting the outside world, and no certainty that rescue would ever come at all. The crew, by most surviving accounts, kept morale intact through deliberate routine, shared tasks, and Shackleton's own relentless insistence that they would, eventually, get home. They did, every single one of them, in one of the more remarkable survival stories in recorded history. But it is worth noting what made that survival possible. A known, if distant, world to return to, a leader devoted entirely to getting them there, and, crucially, an ending. However hard the wait, it was always going to end, one way or another, within those men's own lifetimes. A generation ship offers no such promise to most of the people living and dying inside it. For many, perhaps most, of the people born during the voyage, there would be no homecoming at all, ever. Only the responsibility of continuing the journey on behalf of people not yet born. More recently, in a far more controlled setting, the European Space Agency and Russian researchers ran an experiment called Mars 500, sealing 6 men inside a 550 cubic meter chamber for 520 consecutive days, deliberately simulating the psychological conditions of a round-trip mission to Mars without ever actually leaving Earth. Researchers tracked the crew's sleep, mood, stress levels, and interpersonal conflict throughout, using standardized psychological assessments administered on a weekly basis. The results showed real, measurable, and highly individual responses. Some crew members adapted reasonably well, while others showed clear signs of strain, shifting sleep patterns, and rising tension between crewmates as the isolation continued. And this was a simulation, conducted on Earth, with a guaranteed exit date, full medical support standing by, and the subjects fully aware the entire experience was, in the end, reversible. A real multi-generational voyage to TRAPPIST-1 would offer none of those safety nets to any of the people living through it. Now imagine removing the fixed end date entirely. Imagine isolation not measured in months, with a known and certain return home, but in generations with no return home possible at all, ever, for anyone involved. The people born partway through a multi-generational voyage would never have known Earth firsthand. Their entire understanding of the planet their grandparents left behind would come from recordings, stored data, second-hand stories told by people who themselves were only children when they last breathed unfiltered air. Earth would not simply be far away. It would become something closer to myth, a place believed in rather than remembered. This is, in its own quiet way, one of the more profound costs of the journey and one of the least discussed. We tend to imagine interstellar travel as a triumph of engineering, and in many respects it would have to be. But the engineering, even solved completely, would still produce something stranger and lonelier than most depictions suggest. A closed, sealed society, drifting for decades or centuries through total silence, severed not by malice or accident, but by the basic, unchangeable physics of how fast light itself can travel. Every value, every memory, every reason for making the journey at all would have to survive being passed down, hand to hand, generation to generation, by people who never chose to carry it toward a destination none of them had ever seen with their own eyes. And after all of that, the fuel, the time, the bodies, the silence, there remains finally the question of what would actually be waiting on the other side. After the engines, the fuel, the decades or centuries, the silence, suppose, finally, that a ship actually arrives. What would there be on the other end of all of it to actually find? The first thing any approaching crew would notice is the star itself, and it would look almost nothing like our own sun. TRAPPIST-1 is small enough that, side by side, it would barely outsize the planet Jupiter, and dim enough that it glows a deep, smoldering red, rather than the familiar yellow-white we are used to. From the surface of any of its planets, daylight would carry a quality closer to a perpetual, heavy sunset than to noon. But that dimness comes with a complication that surprised even the scientists who first studied this system closely. Red dwarfs like TRAPPIST-1 were once assumed to be calm, quiet stars, simply because they are so much smaller and cooler than our own. Observation after observation has shown the opposite. TRAPPIST-1 flares far more violently and far more often than researchers originally expected, releasing sudden bursts of radiation that wash over its inner planets with a frequency our own sun, in its current calm phase, simply does not match. Scientists studying the system with the James Webb Space Telescope have found this stellar activity intense enough that it actively complicates the search for atmospheres on the planets themselves, contaminating the very measurements meant to reveal what, if anything, those planets have wrapped around them. The planets themselves carry their own strangeness, born from how closely they orbit their small, dim star. All 7 are believed to be tidally locked, meaning each one always shows the same face to TRAPPIST-1, the way our own moon always shows the same face to Earth. One side of each world would exist in permanent daylight, forever facing that dim red star. The other side would exist in permanent night, facing outward into the dark, possibly cold enough, depending on the planet and its atmosphere, to freeze whatever air might otherwise have circulated there. There would be no sunrise, no sunset, no day stretching into evening the way every human being who has ever lived has experienced it. Only a fixed, unmoving boundary between perpetual light and perpetual dark, with whatever atmosphere the planet holds attempting, weather pattern by weather pattern, to carry warmth from one side to the other. There is something almost geologically poignant about how old this system actually is. Careful analysis of the star itself suggests TRAPPIST-1 is roughly 7.5 billion years old, give or take a couple billion years either way, meaning this entire system of 7 worlds had already existed for billions of years, quietly orbiting in the dark before our own sun and solar system had even finished forming. Whatever these planets are, whatever they hold or do not hold, they are not young. They have had a very long time to become whatever they are going to become. You are listening to these words from somewhere on Earth, under a sky that has never once needed a generation ship to reach the sun warming it, or the air filling your lungs right now without asking anything of you in return. That is easy to forget. It is also, in light of everything this hour has walked through, worth remembering, gently, before you let your mind drift any further. The question this video opened with was never really about TRAPPIST-1. It was about whether a journey like this could ever actually happen. And the honest answer, built from real fuel equations, real biology, real light speed limits, is that it could not. Not with anything we currently have, and likely not with anything we will have for a very long time. The distance was never the true obstacle. The true obstacle was everything that distance quietly asks of a person, or a family, or a civilization willing to attempt it. Fuel that does not exist in usable quantities, bodies not built to survive the crossing, time itself bending in ways that separate who leaves from who arrives, and a silence so complete that Earth itself would slowly become less a memory and more a story, told by people who never saw it. There is a particular kind of comfort, if you let yourself sit with it, in simply not having to decide any of this tonight. No fuel to calculate, no crew to assemble, no grandchildren to commit, sight unseen, to a sealed metal world crossing an ocean of nothing. Just a small red star, very far away, holding its 7 quiet worlds the way it has for billions of years already, asking nothing of you except perhaps a little curiosity before sleep. And yet, somewhere in the patient, decades-long work of pointing telescopes at a small red star in the constellation Aquarius, watching it dim and brighten by fractions too small to notice without exact instruments, something in us kept looking anyway. Not because the odds were good, because looking was the only kind of crossing available to us, for now, and we took it. Picture, if you will, a single point of red light, low on the horizon on a clear night, indistinguishable to the naked eye from 1,000 other faint stars scattered across that same patch of sky. Nothing about it looks closer or stranger or more promising than its neighbors. And yet 7 worlds turn quietly around it, some of them, perhaps, holding thin air and old questions we have not yet answered, waiting in the dark the way they have waited for billions of years before we ever learned to look for them, and the way they will likely keep waiting for a very long time still to come. We may never cross that distance ourselves, but the wondering was never really about getting there. It was about proving, to no one in particular, that we were the kind of species that still wanted to. Sleep well.